Okay, so let's talk about a new data structure. This is priority queue or heap. And we will be talking about the abstract data structure because we are not going to talk about the implementation details. We'll just talk about the features and functions of this data structure. So why this is called a priority queue? You know that a queue actually follows the first in, first out method, right? In a priority queue, the principle it follows is most important out first. That means we use priority queue for specific purpose. Suppose we want to keep data in a data structure and we always want the most important one that we need at the top so that we can just put our hand and grab it. The priority queue is such a data structure which follows this principle. Most important out is first. So for that, how do you compare that which one is the most important one? So the items in the priority queue must be comparable. So the data structure will do some kind of internal sorting to compare items so that it can always keep the most important one at the top. So there might be two kinds of priority queues. One is min priority queue and the other is max priority queue. From the name as it suggests, min priority queue means the minimum priority item is at the top. Max priority queue means the maximum priority item is always at the top. So real life examples might be sometimes I discussed queue, I said like, suppose a printer is connected to different devices and all the devices are sending printing jobs, right? So you can put it in a queue. So first in, first out. But what happens if some of the printing jobs have more priority than the other ones? In that case, we can use a priority queue, right? And put the items in a priority queue so that the highest priority items always remains at the top. And the printer can just take the highest priority items. Okay. So there are two kinds of priority queues, min priority queue and max priority queue. Min priority queue obviously puts the minimum priority item or minimum value item at the top. Max priority queue is the opposite. So the functions are, or the behaviors are, we can add to the priority queue, we can remove a task or item from the priority queue, or we can pick. Pick means we just can take a look at the top, right? Okay, so this is priority queue. We also call it heap. So priority queue actually is implemented on a binary tree. This is very important thing. Binary tree. That means this is what a priority queue looks like. It's a binary tree. That means every node has two children. But the thing is, this is not a binary search tree. You see that here, right? This is a priority queue. But as you see, this is not a binary search tree because in a binary search tree, the left always has to be smaller than the root. But that is not the case here, right? You see that? So this is not a binary search tree, but this is a priority queue. Similarly, this is also another priority queue. And you see that the conditions and the rules of the binary search tree doesn't apply here. But still, this is a priority queue. So this is the first important thing. Priority queue, the first invariant. That means you cannot violate this. For a priority queue, it's built on a binary tree. And then the second invariant, the second condition that you cannot violate is heap invariant. That means every node is less than equal to its children. Remember, we are talking about a mean priority queue now. If you are talking about a max priority queue, everything will be opposite. So instead of less, it will be like greater if you are talking about a max priority queue. Okay, so we don't need to talk about both. We can just keep talking about the mean priority queue or mean heap, and then just the opposite is a max heap. Okay, so we said that if we want to keep the minimum priority item at the top, we always need some kind of calculation or sorting. So that is what is called the heap invariant. That means every node is less than or equal to its children. So let's look at this here. 8. Is it less than its children? Yes, true, right? So this is a valid priority queue. Here, you see 1. Is it less than its children? Yes.
Yes.
2. Is it less than its children? Yes. 3 is also less than its children, right? Okay. So that means this is also a mean heap or mean priority queue. Okay, so next, the third invariant that you cannot violate or third condition to be a priority queue. This is the heap structure invariant. So this is a binary tree, but this one has a very specific structure. A heap, as we said, like priority queue and heap, we are actually using these terms interchangeably. So a heap is always a complete tree. What is a complete tree? So a complete tree is a tree where every level is complete. That means, let's look at this tree. I'm just drawing one tree. Is this a complete tree? No, because there is a space for another node here. Instead of filling that up, I have nodes in the next level, right? So this is not a complete tree. But this is a complete tree. You see on the first level, I can have maximum of 1 node. I have that. In the second level, I can have 2 nodes. In the third level, I can have 2 square, like 4 nodes. It's full. It's a full tree. So it's a complete tree. Here, this is a complete tree. That's why it's a priority queue. Now, you may ask, like, what happens if I may not have like all the nodes. So is this a priority queue? Yes. So a complete tree means, so it's complete, but in the last level, you start from left to right. So this is how a complete tree looks like. You can just think about this structure. So a complete tree is like this. So all the levels are full in the top. And in the final level, if you have less than complete nodes, you have to make sure that all the nodes are in the left. Okay, so let's look at this one. Is this a priority queue? Now you see, if the first variant is binary tree, that's true, right? It's a binary tree. Like none of the nodes have more than 2 children. That is fine. And also now the second invariant, heap invariant, is every node less than or equal to all of its children. Let's see. Is 1 less than 2 and 3? Yes, right?
Yes.
Is 2 less than all its children? 2? Yes. 2
Yes.
is less than all its children, right? What about 22? It's also less than all its children, right? 3? Is 3 less than equal to all its children? Yes, right? 4 is less than its children. 8. 4 is fine. 5 is also less than. Okay, that's fine. So that means the second invariant also passes. What about the third one, the heap structure? A heap has to be a complete tree. Now, Can someone tell me, is this a complete tree? Is this a complete tree? Definition of the complete tree is like none of the levels can be empty except the final level. So all the levels have to be full, but in the lowest, like the lowest level, if you have some empty nodes, like you have to keep up filling from the left. So now see, is it a complete tree? Can anyone answer? Anyone?
I think yes.
No, it's not a
No,
complete tree. You see, I don't have any children here, right? It's missing.
but we have the level 2, we have the nodes, it's not empty.
Yeah,
Level
level 2
1.
is fine, but level 3, you see, level 3, I have nodes in level 4, right? So I cannot keep level 3 empty. Do you see that?
Hmm.
I can just keep some empty nodes in final level, right? I cannot, but is this level the final level?
No.
No. So if I have something here, suppose I had something, say 10, right? Okay. So is it a complete tree now?
No.
No, because
Under 10 we don't have anything.
yeah, so 8, 9 had to be here, right? If in the final level, I can have just, so this should have been 8, this should have been 9, something like this, and this should have been 10, right? So in the final level, I have, say, 5 nodes, and I can accommodate 8 nodes. So if I have 5 nodes, these have to be here, right? Right, from the left. It should have been look like this. Now, is this a complete tree? Someone? Is this a complete tree? Okay, still it's not, because I have to go to the left subtree first, right? So I cannot come from the right subtree. So left subtree, and then this is right. It cannot be the right subtree. Is it clear to everyone that now this is a complete tree? Yes?
Yeah.
Okay. Okay, so 3 invariants, very important for a heap to be a valid heap or priority queue. Okay, next. Now the operations pick or pick mean. So since we are talking about a min heap, right? What pick mean does, it looks at the top and returns the value. It doesn't do anything else. So simply return the value at the root. And it's a constant time operation, obviously, because I just take a look at the top. So this is order of 1. Simple, right?
Yes.
Pick min. Next, remove min. So this is another operation that I may need to do, like removing the min item. So removing is easy, like, because this is a min heap, so I remove the minimum item. That's fine. But the thing is, now the structure is broken, right? So once I removed one item, now the tree structure is broken because I have taken out the root. So I have to fix the tree structure. And we know that a priority queue always has to be a complete binary tree, right? Okay. So if I want to make a complete binary tree, let's do this thing. Only place we can take a node out. So we have to take another node out. and put it into as the root, right? So if I want to keep it complete, the only place I can take the node is from this one, right? I can only take this one. Is it clear to you? To keep it a complete tree, to make it a complete tree, or keep it a complete tree, right? So the structure is broken. So what I do is I take the last node from the final level and put it in the top. Okay. Now, is it a complete tree now? Yes.
But 13 is higher than 4 and
Yeah,
7.
that's yes. This is a complete tree, but another invariant is violating, right? Yes. Okay. So now it has like, okay. So now heap invariant that is broken, right? Because heap invariant says that the root node has to be smaller than its children. So now let's fix that. So that means uh, when I'm removing, first removing is easy, done. Now the tree invariant is broken. Second, what I do is I take the last node, put it in the root, and make it a complete tree. Now the second heap structure invariant is also done. But the thing is, the heap invariant is now violated because 13 here is not the largest. Okay, so what do I do? I have to fix it. How do I fix it? We call it bubble down. Okay, so let's very carefully look at this animation. So 13 is the problematic node here. So we recursively swap the parent with the smallest child. So 13's child are 4 and 7, right? So what is the smallest child among 4 and 7? 4, right? So we make a swap between 13 and 4. Okay. Okay, next. 13 is still problematic, right? Okay.
Yeah.
So 13's new children are 5 and 8. And 5 is the smallest, right? So I make a swap. Okay. Is 13 still problematic?
Yes.
Yes. So I make a swap between 13 and 11. So does the bubble down, does it make sense now? Like a bubble is actually going down, right? It went down. Actually, bubble doesn't go down. It goes up, but think like a special kind of bubble that goes down, right? In okay. So we are bubbling down, and now you see the structure is restored. Okay, so what did we do? We first we found the last element, which was here. We took it at the top, right? So we found the last element, moved it to the top, and swapped until the invariant is restored. Is it clear to everyone? Okay. Next, uh, the question is, when I was bubbling down, why I chose the smallest child? So look at this one. So you see that when I swapped, if I had swapped 13 with 7, right? What the issue would have been there? Again, there would have been a problem, right? 7 goes here, 13 goes here. Is it fine? Is it like, again, we had a conflict between 7 with 4, right? 7 is greater than 4. So that means that's why when we were bubbling down, we were swapping with the smallest child. Okay. Yeah. So okay, one question I have here. We know we already told you that a heap is a complete binary tree, right? So complete binary tree. So it's a tree looking like this. So this is a heap. Can someone tell me if there are like n nodes in the heap or n nodes in this tree, what is the height of this tree?
n-1.
No, this is a complete tree. That means it's a balanced tree. You can think like a balanced tree or something like that. It's log n. That's the height, right? Because if it's not complete, this is also a tree, right? This is n nodes, and the height is also n or n-1, whatever, right? But a heap is always a complete tree. That means I can say that a complete tree is a like more or less a balanced tree. And if that is the case, then the height is always like, height is never going like crazy down, right? It's always like you are some kind of restructuring and keeping it like this structure, right? Or maximum if you're adding a level, still this structure is actually maintained. It's never going like this. Can you see that? So the height of this is log n. Think about it. If it's not clear to you, think about it, because this is like a very proper tree. A heap is a very proper kind of tree where you keep on filling up every level. That means you are putting every node at the shallow level. You are not letting it go crazy down, right? So the height of the tree is log n. So this is important because I will tell you why this is important. Okay, let's talk about the add algorithm. So when I'm adding something, suppose I want to add a node. Tell me, suppose I want to add 3. Can someone tell me where do I add? Just simply I want to add. Can I add here? Can I add here? Can I add 3 here?
Yes.
In that case, is it a complete tree?
No, it's not. It's not.
Yeah. So why do I have to add? Can I add here?
No.
No.
Nine.
Yes, so I can add here, right? Can I add here? Just
Yes.
think like,
Yes.
okay, I'm adding here, but this is not its right place, right? So what I have to do is I have to do bubble up. Okay, so insert the node at the bottom level to ensure that there is no gaps. That means make sure that this is still a complete tree. Okay, that's fine. Then that means this is the place where I have to add this circle. I am adding there. Then fix heap invariant. Structure invariant is fine now, but heap invariant says that parent has to be smaller than the child. So I have to bubble up. So do you see that this is a problem with this, right? I have to swap on with parent until your parent is smaller than you. So 3 is swapped with 8. Now still there is a problem. You see 3 is smaller than its parent 4. That cannot be true. So I swap it again. This time it's fine. So I keep on swapping up until I am smaller than my parent. Okay. Okay, so tell me, if you are adding something, what is the runtime? How many times maximum? How many swaps you do? How many maximum number of swaps you may need to do after adding something? What is the height of the tree with n logs, n nodes?
Log n.
Log n, right? So that means how many swaps maximum I have to do? Log n number of swaps, right?
Log n.
Yeah, it's clear, right? So it's order of log n. Adding an element to a heap. Obviously, I just think that you know the where you have to add. You keep track of the place where you have to add. If you know that, then in the worst case, you have to do log n swaps, and the heap is restored. So the worst case runtime of an add operation is log n, right?
Log n.
Yes. Similarly, even for remove, the worst case is log n. Just think about it yourself. Okay. So, okay, let's see. When I'm removing the node, right? And then what I was doing, I was finding the last node and swapping it to the top, taking it to the top and then bubbling down, right? How much I can bubble down maximum? Log n, right?
Log n.
Yeah, so the remove mean was log n. Okay. So in this course, we are not talking much about the best case. We don't need that. Just think about the worst case, because that is the complexity of the or performance of the algorithm. And once we are doing the adding, we are just, instead of bubbling down, now we are just adding to the last position and bubbling up. So that is also log n. Okay, so min heap runtimes are remove is log n, add is log n, and then we also talked about another operation, that is peek. In peek, we don't do anything. We just take a look at the top. That was order of 1, constant time, right? Okay. Okay, so how do I implement heap? One very simple implementation of heap is using an array. I am going to show you. Because in an array, it's easy to make a very nice kind of parent-child relationship. So you have a heap here, and this is the array representation of the heap. So how do you do this? Very simple. A, right, like this: A, B, C, D, E, F, G, H, I, J, K, L. So go to every level, just read from left to right, put it into the array. Okay, and then it will actually have a nice heap kind of a structure. I'm going to show you how. Okay, so let's think about this. In an array, we know the index, right? Let's show you from here. We know the index of each array, of each location. Index starts from 0. Okay, so let's do this thing. In your array, keep the 0th index empty or something. Just, it will actually, you can actually start from 0th index, that's fine. But if you keep the 0th index empty, it will look a little bit more neat. Okay, so this is index 1. Tell me, what is the children of index 1? 2 and 3, right? So can I say that if my index is I, my left child's index is 2i, and right child's index is 2i plus 1. Okay, let's see if it works. What about here? What is the index here? 4, right? Does 4 means that 2 into 2? Does this 2i thing translate here? Does it do? Yes. What about this? 2i plus 1. Is it 5? 2i plus 1. 2 into 2 plus 1. What about this? 3. This is a left child, right? So 3 into 2. 3 into 2 is 6, right? So is 2i thing working here? Is 2i plus 1 thing working here? 7, right? So now you see that in an array, now I can say, oh, okay, index 1. Oh, the children is going to be, sorry, okay. So the left child is going to be 2 into 1, and the right child is going to be 2 into 1 plus 1, 3. Okay, and then someone says, oh, okay, so what is the left child of, say, 3, or right child of 3? Right child of 3 is going to be 3 into 2 plus 1, 6 plus 1, 7. So this is going to be the right child of C. Do you see that? So using an array is so simple. Okay, so if you keep the first space empty, what happens is left child of I is going to be 2i, right child of I is going to be 2i plus 1. Similarly, it's easy to find any parent. Say someone says, okay, find me the parent of 11. What I do, I just divide it by 2. Okay, 11 over 2 is, round it up, like scale, round down, 5. What is the parent of, so this was 11, right? What is the parent of 10? 10 over 2 equals to 5. So this was 10, index 10. Its parent is 5. So you see, even if I keep it in an array, there is such a nice relationship between the indices. Someone says, okay, now, okay, fine, I got it. You put it into the array. Now do this thing for me. Do a pick. Simple. I just go to the index 1. That is the pick. Do the last node. Yeah, I have to keep size of the array. Okay. And why do I add the new node? Add to the size plus 1th position. Fine. Okay. So if someone asks, like, when we are actually doing remove operation from the array, when we are doing the add operation to the, remove operation from the heap, we are doing the add operation to the heap. We always said, go to the last element and add there, or take it to the top. How do I get the last element? If I put in an array and always I keep track of the size of the array, then I can just go to that location and that's the last element. Okay, so, and obviously now the question is, hey, how do I do remove? I have put everything in array. Now help me, I want to add something, I want to remove something, and is it going to have the same runtime? Yes.
Yes.
Yes. So say someone wants to add something into the array, say something here, right? Something, I know that I have to add here because I know the size of the array. So I know, okay, next I have to, after add, we do bubble up. So how do I bubble up? I know that 7 has to compare with 3 because 3 is the parent, right? So compare here, do bubble up, fine. 3 has to compare with 1, bubble up. So you see, I'm jumping from index to index and still keeping this log n, right? Okay. So array is a very good implementation of heap. Using array, I can actually make a good implementation of the heap. Obviously, using a tree structure is more obvious, but it's also I can use an array and just play with the indices and do all the operations with the same runtime. Okay. Yes. And also sometimes it's even better because you can just jump around very easily, right?